Welcome back, AP Calc. We are going to hit the last two examples, which will be examples 12 and 13, with the natural log function involved in some kind of integration. So I have a definite integral here for example 12, and we're going from 0 to pi over 4. I have the square root function of 1 plus tangent squared x with respect to x. And I'm looking at this, and I'm seeing one of those Pythagorean identities here that I know. So you need to, if you don't know it off the top of your head, then you're going to have to derive it, but you have to recognize that this 1 plus tangent squared x, the fact that it's squared keys me into it. Because 1 is really 1 squared and tangent squared. You got a couple of squares playing around with the addition. And so I'm thinking of that Pythagorean identity. That is the most basic trigonometric Pythagorean identity that we have. And I'm talking about the one that says sine squared of theta plus cosine squared theta is equal to the number 1, which is 1 squared, but it's still plain old 1. And that comes off your unit circle, just the fact that the x squared plus the y squared is equal to the r squared. So I want to get the tangent function involved in this, and I know that the tangent function is a sine function divided by the cosine function. So I'm going to do a division here with cosine. However, I know that I want tangent squared as well, so I'm going to use a cosine squared so that I can build the tangent squared. So I'm going to divide each and every term by cosine squared theta, cosine squared theta, cosine squared theta. And sine squared theta divided by cosine squared theta is going to give me that tangent squared theta I'm looking for. Plus cosine squared theta divided by itself is the number 1. And then 1 divided by cosine squared theta is the cosine. Cosine has a reciprocal of secant, so 1 over cosine would equal secant, 1 over cosine squared would equal secant squared theta. And I'm looking at this, it looks backwards, but I could turn it around easily enough. Tangent squared theta equals secant squared theta. And the theta is just a dummy variable. It could be any angle variable you want to use. I use theta because that's how I learned the formula myself. But it could very well be x's. So 1 plus tangent squared x is going to turn into secant squared x. And I'm going to rewrite my integral from 0 to pi over 4. The square root of secant squared x with respect to x. The square root function and the square function counteract each other, and you're just down to just plain old secant of x. And we integrated the secant of x in one of the earlier videos, and we had the fact that it was going to equal the natural log function of the absolute value of secant of x plus the tangent of x. Alright, and we're going to evaluate this between 0 and pi over 4. I'm going to wrap this in parentheses like this, and I'm going to go from 0 to pi over 4. And instead of drawing a bar up and down, because that looks a little funky, it's just accepted mathematically to put your 0 on the bottom of the bracket and your pi over 4 on the top of the bracket as well. It's kind of like you're using the bar of the bracket to indicate that bar that typically holds your lower and upper limit. Okay, now we have to apply the fundamental theorem of calculus and say we have to continue applying it because we've already integrated. And we're going to have 2 sets of brackets here, one with our pi over 4 substituted into all of this, and one with our 0 substituted into all of this. So this is natural log of the absolute value of secant something plus tangent something. Those are my absolute values. Same thing happens over here. Natural log of the absolute value of secant of something plus tangent of something. Close my absolute values. And my first something is my upper limit, pi over 4. Put that everywhere you see your parentheses in the first set of brackets. And a 0 goes in everywhere you see set of parentheses in your second set of brackets. And now we need to do some trig work here. Pi over 4 is in quadrant 1. So we're looking at a quadrant 1 reference angle. Pi over 4 is 45 degrees. Ratio of the sides 1, 1, root 2. And I'm looking for the secant of pi over 4. Secant of pi over 4. The secant is the reciprocal of the cosine function. So instead of looking for adjacent leg over hypotenuse, we're going to pick up the hypotenuse over the adjacent leg. That's going to give me the square root of 2 over 1, or just the square root of 2. So I will now have natural log of the absolute value of the square root of 2 plus tangent of pi over 4. The tangent function compares the opposite leg to the adjacent leg. So the tangent of pi over 4 is 1 over 1, which is just plain old 1. Close my absolute values, close my bracket. Although my absolute values aren't serving any purpose here right now, seeing as the square root of 2 and 1 are both positive anyway, minus, bracket, natural log of the absolute value. I need the secant of 0 and the tangent of 0. Well, I can do that a couple of different ways. I can look at one of my quadrantal angles on my unit circle, which has the point 1 comma 0 here. And we know that anywhere around our unit circle, I know I'm not drawing the circle, I'm just kind of like motioning it for it. Anywhere around the circle is the cosine of the angle that you're at, and then the sine of the angle that you're at. So the cosine of 0 is 1, the sine of 0 is 0. Another way, if you don't like looking at your unit circle, is you could actually look at what the cosine function looks like between 0 and 2 pi. Cosine function starts up here at 1, ends at 1, halfway in the middle it's down at negative 1, and it goes something like this. So the cosine of 0 is up here at 1. Either way, use your unit circle or use your graph, it doesn't matter. And the sine graph between 0 and 2 pi starts at 0, ends at 0, halfway in the middle it's also at 0. Halfway between its first two zeros it hits a high, halfway between its last two zeros it hits a low. Goes like this. And there's your sine graph, so the sine of 0 is 0, as we see right here. Okay? So secant of 0, get back to our problem. Secant of 0, that's the reciprocal of cosine of 0. The cosine of 0 is 1, either from here or from here. Cosine of 0 is 1, and you reciprocate that, you still get a 1. Plus the tangent of 0. If I'm looking for the tangent of 0, I have to look for the sine of 0 divided by the cosine of 0. The sine of 0 is 0, and the cosine of 0 is 1, and 0 divided by 1 is 0, so therefore the tangent of 0 is 0. Close my absolute values, close my bracket. Again, these absolute values are useless right there. Okay, so I'm going to erase what I did right here a little bit. And we're going to bring this up. And this is going to say natural log, parentheses this time. I don't need the bracket, the absolute values for positive values. And I'm going to turn that around so it says 1 plus root 2. Just because in case anybody gets sloppy while they're copying, I don't want anybody to accidentally make this plus 1 look like it's underneath that radical sign, because it shouldn't be. So I'm going to write it first, and then we'll alleviate that possibility. Okay, minus the natural log of 1 plus 0 is plain old 1 here. Okay, so this gives me natural log of 1 plus the square root of 2 minus. And what is the natural log of 1? Or better yet, e to what exponent would equal a 1 when that exponent is 0? So this just gives me natural log of 1 plus the square root of 2, and there's no way for me to really check that without a graphing calculator or some utility. I could just walk through my work and make sure I didn't make any errors, but this is the answer I'm looking for. It represents the area bounded by the curve of the square root of 1 plus tangent squared x in between x equals 0, x equals pi over 4, and the x-axis. Alrighty, so much for question 12. 13 is actually where it gets a little difficult. Turns into an easy problem, but it certainly doesn't look like an easy problem to begin with. So, that hopefully should teach you a lesson in perseverance. I need you to stick with a problem. Try something else if the first thing doesn't work, and just don't quit on it. Okay? Alright. Here's example 13, our last and final example on 5.2. We are looking at the integral of 1 over 1 plus the square root of 2x with respect to x. And I'm purposely throwing that square root in the denominator for you. Alright? Even me, I'm looking at this question and I'm saying, what? I'm supposed to be given an example of a natural log problem in an integral, and I'm looking at this? I see that I could use my u just fine if I let all of this become a u, but where would my du be? I don't even see a du anywhere in the problem. All I have is a dx. So it's very complicated looking to me. I can't really wrap my mind around it. As a matter of fact, I don't even know what I can do. I'm looking at this thing and nothing is really coming to mind, but I know that my teacher's going to be mad if I don't see an effort on that paper, or if she doesn't see an effort on that paper. It's me. So I'm going to go to the side anyway. I'm going to just try something. I'm going to say let u equal, that was weird, let u equal 1 plus the square root of 2x. So this is u is equal to 1 plus 2x, quantity to the 1/2. And I'm going to go ahead and take its derivative and see what happens. I'm going to say du is equal to 0 plus, I'm going to use my power rule here, 1/2 times the quantity of 2x to the negative 1/2 times 2. That's my chain rule right there. All with respect to x. Alright. So my du is, I'm not going to write the 0. This 1/2 and the 2 that's way over here counteract each other. This 1/2 and that 2 don't, though. Be careful. This 2 is wrapped in parentheses where some funky exponent is being applied to it. So this is 2x quantity to the negative 1/2 with respect to x, which is 1 over the square root of 2x with respect to x. 1 over because of the negative symbol, the square root sign because of the 1/2 exponent. So this looks crazy. Okay, I could come over here and I could say, yeah, this whole thing is going to be my u, but then I want to circle the dx and put something in terms of u in it. Sorry about that, you guys. That should be a du. So I want to come back over here and put my dx in terms of u, but I look at dx over here and it's a mess. I mean, how would I solve for dx and get it all by itself here? It would be the square root of 2x times du, right? But I can't mix my x's and u's if I do a substitution up in here. This, by the time I'm done, this integrand with my dx, everything has to be totally in terms of u. So now my question is, can I get this square root of 2x written in terms of u? And the answer is absolutely. You can take a look at the original u substitution that you did. U is equal to 1 plus the square root of 2x. So if I subtract 1 from both sides of my equation, I get u minus 1 is the square root of 2x. You can turn that around if you feel like it. Square root of 2x is equal to u minus 1. So instead of the square root of 2x, I can replace that with the quantity of u minus 1, which will allow my dx to now be written totally in terms of u, which means I can do this substitution up here as a u minus 1 du in place of my dx. And this, believe it or not, is going to turn into a really nice problem. I'm going to have a u on the denominator, I have a u minus 1 on the numerator with respect to u. This is one of those polynomial over monomial things, but you have a binomial, just a type of polynomial. We're basically going to split this up into u over u minus 1 over u, all with respect to u. Take one more step, simplify just a little bit more, which you probably could have done from there. Now what's the integral of the number 1 with respect to u? It's u. And what's the integral of 1 over u with respect to u? That's your natural log of the absolute value of u. And I need a plus c because this is an indefinite integral. I don't know what numbers I'm plugging in, so I have to account for all of them here and put my plus c. So my u was 1 plus the square root of 2x minus the natural log of 1 plus the square root of 2x plus whatever my constant is on the end. And that is my answer. That is what I get for my final answer. So I'm going to erase all that u substitution over there on the left hand, on the right hand side of the board, and I am going to put my check there. All right. Okay. So here we go with our check. I want to take the derivative with respect to x of anything I just boxed right there and said was my final answer. So 1 plus the square root of 2x minus the natural log of the absolute value of 1 plus the square root of 2x. Close my absolute values, plus c, close my bracket. And I'm going to take this derivative. So the derivative of 1 with respect to x is 0. And this derivative here, let's not forget what that is. I'm just going to come to the side for that for a minute again. This is equal to the square root of, square root of 2x. So it's 2x quantity to the 1/2. Now when I take this derivative, I'm going to end up getting 1/2 2x to the negative 1/2 times that 2 again. The 2's will divide off, and I'll have 1 over the square root of 2x. So let's not forget that. I'm going to use that thought process here. Alright, so right up here, I'm just going to hit this piece of it, okay? So 1/2 2x to the negative 1/2 times 2 minus, now I need to take the derivative of a natural logarithm, so I know I'm coming into a fraction. Whatever the natural log is applied to, that's my u, so to speak. It comes into the denominator, and then I take the derivative of the denominator and I put that on the numerator. So the derivative of 1 is 0, plus, and the derivative of that square root of 2x again, see it here, is going to come back down to this, 1/2 times 2x to the negative 1/2 times 2. And the derivative of this constant is, of course, 0. This gives me, I'm not going to write the 0, half of 2 is gone, so I just have 2x to the negative 1/2 minus, this 0 is gone, and I have, again, 2x to the negative 1/2 over 1 plus the square root of 2x. So this has to get simplified down. I can't leave negative exponents here. So this is 1 over the square root of 2x, which I knew it was, minus, and this can get a little tricky, a little hairy with you here, but I'm going to do this, 1 over the square root of 2x, and now divided by 1 plus the square root of 2x. I'm going to copy this for a minute, square root of 2x, minus, this square root of 2x can come down and join this denominator. And this is 1 over the square root of 2x. Oh, my square root symbols are going so high. 1 plus the square root of 2x. And I only have one fraction in my original question, so I have 2 here. I'm going to build a common denominator and put them together. My common denominator will be 1 plus the square root of 2x multiplied by the square root of 2x. So I need a 1 plus root 2x here. 1 plus root 2x there. Okay, I can see this working out really nice at this stage. I have a common denominator here. It's going to have a square root of 2x. It's also going to have a 1 plus the square root of 2x. My numerator here will be 1 plus the square root of 2x times 1, which is just 1 plus the square root of 2x. Copy my minus sign. Copy my 1 because I don't need to manipulate this fraction at all. It already has the common denominator. My negative 1 and my positive 1 counteract each other. They're opposites. They spontaneously combust when you put them together. And I end up with the square root of 2x divided by the square root of 2x multiplied by 1 plus the square root of 2x. These divide off, leaving me with 1's, and I have 1 over 1 plus the square root of 2x, which is indeed the exact same integrand that I started with. So I am pretty much good to go with a check right there, and I am done. You're done. I know you've had a few videos. I've been doing them over and over myself, so talent out.